I'm delighted to introduce Dr. Todd Krauss, who is a professor of chemistry and optics at the University of Rochester and currently serves as the chair of the Department of Chemistry. Dr. Krauss received his Bachelor of Science, Master of Science, and PhD in applied physics and engineering, all from Cornell University. He got his PhD in 1998 and served as a postdoctoral research fellow at Columbia University in chemistry from 1998 to 2000. In 2000, Dr. Krauss joined the chemistry faculty at the University of Rochester as an assistant professor. In 2006, he was promoted to the rank of associate professor, and in 2008, he received a joint appointment in the Institute of Optics. In 2010, Dr. Krauss was promoted to full professor and assumed directorship of the Rochester Advanced Materials Program, formerly the Materials Science Graduate Program, for 3 years. Dr. Krauss became chair of the Department of Chemistry in 2013 and has served in this role for 9 years now. Dr. Krauss chaired the Center for Energy and the Environment Structure Subcommittee in 2014-2015. Todd's research interests involve fundamental studies of materials at the nanometer scale down to single molecule level, with specific emphasis on colloidal semiconductor nanoparticles such as semiconductor nanocrystals or carbon nanotubes. Dr. Krauss is a recipient of a number of prestigious grants, including from the NSF and the DOE. He has published over 100 publications and is a fellow of the Optical Society and the American Association for Advancement of Science. Without further ado, Dr. Krauss.
Igor, thanks so much for that kind introduction. Thanks to you and Adam for the invitation. It's great to be here. I noticed you were smiling when you said chair for 9 years, you know, like we've survived the torture. We're at this point.
That's truly impressive.
We're immune to any more pain, but thankfully that will end soon. Let me see if I can successfully share the screen. So did that work?
It did.
Okay. Let me see if I can get a laser pointer and then we're all good to go here. All right, perfect. So it's great to be visiting Alabama virtually. That's the one great thing about Zoom. Wish I could be there, you know, in person to see you all, but it's good to, you know, be able to do this over the internet, and I'll see at least the digital representations of you at some point. So I want to tell you a story today about something new actually in our group, and these are things called polaritons. And so, you know, a few years ago, we didn't have much knowledge of polaritons. We've gotten a little bit more familiar with them. They are, as we'll talk about in the next, you know, few minutes, hybrid light matter interactions, you know, so they're a little different because normally when we think of light in chemistry, we're using light to do some spectroscopy experiment, right? Here, light is actually forming some part of the quasi-particle state. And so we're in particular interested in using nanoplatelets of cadmium selenide and these dielectric cavities, laser cavities, essentially, to make these polaritons. And we'll get into what that is in a minute. But I want to thank those who really were responsible for what we did. So this is a collaboration that is still continuing and expanding, actually, into several different tentacles. So on the experimental side, in optics is Nick Vamavakis and his student Lang Yu, who really did all the work. So Lang Yu made all of the measurements you're going to see on the polaritons, all the angle resolve, photoluminescence, and reflectivity. That was him. And then on the theory side, you know, we're really fortunate to have Peng-Fo Huo, Frank Huo at Rochester, and he's been a fantastic theorist and has spent a lot of he's an assistant professor his pre-tenure period looking at polaritons in their physics. And Arkajit was a spectacular student, did all the calculations you're going to see. And then in our group, you know, we had Ovacek, who's in the obligatory, you know, Zoom photo. He's down there. So Ovacek put together these cavities, and it took a long time to actually get the nanoparticles into the cavities and get some decent measurements. Mahelet is not in the image. She was out on maternity leave for this shot. But Willie also was in this shot, and Willie provided the platelets. So in terms of outline, what we'll talk about, I want to catch everyone up on some properties of nanoplatelets, in particular their electronic states, so we can interpret the latter images, with a reasonable affinity. And then really want to discuss why we, of all things, to stuff into a laser cavity, why did we go after these nanoplatelets? Why didn't we pick something else? We had some good reasons for that, we think. I want to spend most of the time talking about these things called polaritons, right? This is a diagram here on the left of what a polariton is. You can imagine for atoms, let's just say with grounded and excited states, the most simplest situation, if you put an atom in a cavity, you start to hybridize these two with the photons in the cavity, and you get these hybrid, as we tried to diagram here in this cartoon, light matter interaction. So we want to explain a little bit about how polaritons work for molecules or nano objects, and some spectroscopy and then some simulations to get some really physical insight. And then I want to finish up by telling you a little bit about some applications where we're using polaritons to actually do some new chemistry. So what we're using in these cavities are cadmium selenide nanoplatelets. So the cadmium selenide quantum dots, we've been studying them in our group for a long time, right? And they've been around for 40 plus years now, right? These are similar in that they're little colloidal objects that are coated with oleic acid in this case, making them very hydrophobic. And they're made similar to the quantum dots. In this case, you put a chalcogen precursor, so in our case, a selenium, let's say, in some high boiling point solvent like the oxidecene, and then you throw in a cadmium precursor. And here you would use cadmium oleate for quantum dots. We add a little bit of acetate, and that helps form the platelets at some pretty high temperature. So you can control the thickness somewhat by the temperature. You get very highly crystalline, single crystalline plates. And if you were doing this for quantum dots, you would get a size distribution that's about 5% is like the best you can do. There's always some atoms sticking out of the dot, somewhere that leads to this size distribution. But the nice thing about the platelets and what attracted us to them was that they're really in the thin direction. There is almost no distribution in size. Okay? It's extremely monodispersed. And so this was very attractive for a number of reasons, as we'll show you in a minute. Also, this means that these surfaces, these 001 surfaces, right, are extremely well defined, which allows us to start to get a handle on some of their surface chemistry. So the platelets we use are square. You can see them in the TM image here. They kind of look like little napkins, right? They're about 20 by 20 nanometers on a side, and we can make several different thicknesses. And again, these aren't our syntheses, and we borrow the syntheses, but you can make. We've gotten it down to 2, 3, 4, 5, or 6 monolayers. Mostly here, we're going to use the 4 ones, but we actually sometimes will label them by half monolayer because the top and bottom surfaces, those 001 surfaces are all metal, all cadmium in our case. And occasionally you can see a platelet turned on its side, and then you can get a nice, TM image, and you can see the columns of atoms through the platelet and things like that to measure thickness exactly. Right? So these are what we're going to be using, these sort of square napkin-like nanoparticles. Okay, so in order to understand polaritons, we have to first understand excitons in platelets. And so the conduction band of a platelet, really its origin, if you were thinking about it from a chemical perspective, comes from the cadmium 5s orbital. So there's really only one state here contributing to this band. However, the valence band is from the selenium 4p orbitals, right? And so for those, we just talked about general chemistry earlier, I should confess, since I was, as Igor mentioned, I was an applied engineering physics major throughout my entire training, so including PhD, right? So I never took general chemistry. I placed out. So I do sympathize with some of the students who want to place out of general chemistry and not care about it. But remember your general chemistry P orbitals, there's 3 of them, Px, Py, Pz. So this should contribute to 3 bands in the valence band. And that's what we see. So if you go through, and this is a model by Sasha Efros and Benoit Duboutre contribute to this paper about 10 years ago now, right? You can go through and first just model the band structure of bulk cadmium selenide, and you see you have this one conduction band and these 3 closely spaced valence bands. And then if you start to think about, now we're going to confine these bands and make nanoplatelets, what you're actually doing as you make The platelet is you're restricting the Brion zone to wave, essentially to wave vectors about 0, right? So in other words, you can't have a really long wavelength exciton in a platelet that's only 20 nanometers. So you start to restrict more and more space around k = 0. So as you make the platelets thinner and thinner and thinner, you start marching out here, let's say to the left in reciprocal space, in k space, right? And so if you start to think about what are the energy, like the lowest energy bands and an energy gap of the platelets, the larger platelets have an energy gap, between this heavy hole band and then the conduction band, right? And then as you make the platelet thinner, you start to march things out and the band gap gets bigger. There are also optically allowed transitions from the light hole band. And so I marked those with these triangles. And so in an absorption spectrum, and these are both strongly optically allowed. So an absorption spectrum, what you normally would see is a transition, the band gap from the heavy hole to the conduction band, and then you would see a second transition from the light hole. Right? So that's what you would predict. And then these transitions would get blue shift and spread apart in energy as you make the platelets thinner. Right? So that's what you get. This is from this not our work from this paper, but I stole this figure because it's really nicely illustrates the different thickness platelets and how you can kind of get all the colors from kind of the blue green out to the red. This is our spectra for 3.5 and 4.5 monolayer platelets. The absorption is in the purple and red, and then the blue and green respectively is the photoluminescence. And you can see that you can get these beautiful transitions, right? These heavy hole and light hole absorption transitions, and then you get luminescence from the heavy hole state of the platelet. Very, very small Stokes shift, very narrow spectra, right? Extremely narrow. And this was a little surprising to us, right? But I think this really just reflects the fact that, because we're so used to seeing quantum dots, right? Where there's just a big inhomogeneous distribution of sizes. This just reflects the fact that the platelets are all the same thickness. And you can prove that to yourself if you start doing single molecule spectra. So, you can measure ensemble full width half max. Let's just take the 4.5 monolayer ones that are like under 9 nanometers in the green. And so that's for example, the red curve here. And if you start hunting for single emission from single platelets, you can see that, and it's the noisy blue curve here. And the ensemble is only about 10% wider, right? So it's remarkable that that really it's starting to look more like one would consider to be a molecule, right? Where all the states have the same width. Now, why do we care about the width of these lines? Well, when you start forming polaritons, it turns out that the width is important because of this thing here. So in a simple atomic picture, when you start hybridizing an energy state, electronic state, with the photon state, the quantized photon state in the cavity, you get these two states forming, right? And so they're separated by something called the Rabi splitting, and we'll get more into that in a minute. But if you're starting to form two states, as you go from like in free space, you have, let's say, one state, and in the intracavity, you have two states. Your ability to distinguish the separation of these two states from the one state, right, depends on the line width. So, if you have these really broad lines, it's going to be very hard to see exactly when you form a polariton. Whereas if the lines are really narrow, then it's much easier. It does make it a bit more difficult to actually hit resonances in cavities, as we'll see, if the peaks are narrow, but we can work with that. So the narrow photoluminescence spectra was one reason why we really wanted to go after platelets as opposed to quantum dots. Also, another factor that we were considering was the transition dipole, right? So, or oscillator strength, depending on your field. The transition dipole is in the plane of the platelet, and it's huge, right? It's really large, even compared to quantum dots, a few times larger than quantum dots, which are a few times larger than organics. So the combination of narrow spectra and really large oscillator strength should allow us, in principle, to have to see strong coupling to the cavity easier. Now, eventually, we like to do chemistry, you mentioned in the introduction to this, with these polaritons. And so having your electron or exciton sit in the excited state for a reasonable amount of time, people speculate, would allow you to do things like maybe polariton singlet fission or increased polariton charge transfer, energy transfer. And we'll talk about charge transfer at the end. But platelets have a reasonably long lifetime of, a few nanoseconds. It's not as long as some things like quantum dots, but it's longer than dye molecules, or in our lab, we look carbon nanotubes that are really short. So we thought that this reasonably long lifetime would give us a shot at seeing strong coupling. Now, we're not the only ones by any means that have thought that platelets may be good for forming polaritons. There's a few papers out there, and I'll share some with you. So there's been some people put platelets in this optical cavity here. It's 2 metal mirrors, and they put the platelets on the mirror, which it isn't great for coupling. But what made this experiment really impressive, it's like remarkable, is that they put one of the mirrors on a stage, and so they're actually able to translate this right mirror in and out, which allows you to tune the cavity length, and therefore tune the coupling, right? And so they actually did end up seeing strong coupling, but in terms of making something that could be reproduced on a large scale, this would not be the way to go. It's like a hero experiment, right? It's like a one-off experiment, very tough to do. So we don't want to pursue that approach. Probably more amenable to kind of reproduction, reproducibility is this geometry, where you can use the plasmonic cavity, the light bouncing around in this thin film of gold with the platelets on top to get you strong coupling between the plasmon and the gold film. And they got 50 MeV Rabi splitting, which is the strength of the coupling. So that's not bad, but it's a challenge to get. Those of you who work with metal nanoparticles or metal films know they're pretty lossy, right? So it's really a challenge to get high quality factor cavities. Quality factor being a measure of how long the photons are in resonance in the cavity. And the photons just don't last very long in these metal cavities. Now, this is work out of Dave Norris's lab, I believe, and they used a similar approach, but instead of actually just having a straight metal film, they put holes in it and then put the platelets on top. And the array of holes actually gave you this kind of collective effect. And then they used it to get pretty large Rabi splitting in reflectance. But again, using these metal cavities, it's really hard to get high quality factor, and you end up saturating the light matter coupling strength, right? You really can't go much higher than this. So we chose a different approach. We wanted to go after dielectric cavities because we thought that they had a better potential to get high quality factor, and potentially then that could be better for our applications in chemistry. So we naively went, we'll fabricate a cavity, right? The professor always says it's like afternoon experiment, right? We thought maybe like 1 month experiment to do this, and it was a lot more challenging than that. But let me show you how we ended up doing it. So we went down to Cornell and deposited a distributed Bragg reflector. It's either alternating dielectric layers to perform like a really high reflective mirror on a piece of silicon. And then Overcheck, spun some polymer, PMMA, with the nanoplatelets in it at really high concentration. We wanted as many platelets as we could in there. And then we put silver on top. Now, and the silver thickness was variable. When we wanted higher quality factor cavities, we made a thicker silver, but the price we paid for that was reduced transmission, which meant reduced ability to see things like photoluminescence or from the cavity. And so we often compromise with, and 35 nanometers was kind of a compromise value. We're looking at exciton polaritons. That's what our goal is, trying to form those. And so the excitons have these wavelengths on the order in the green, on the order of a couple EV, 2.5 EV or something. And so therefore something with a wavelength of 500 nanometers, you want to have a fundamental mode of your cavity that's roughly half wavelength. And so that's why this distance here is only 180 nanometers. And it's a bit challenging to get it to be that thin and reproducible. So, and then we put SiO2 on top, put some silica on top just to protect it from oxygen. So, when we just made the cavities, everything was pretty straightforward. PMMA is a beautiful material. It's a resist, right? It's optically very clear, great material to use, and that was fine. The problem is when you put the platelets inside the PMMA, now you've changed the chemistry there, right? And often what we got was this film on the left. We got platelets aggregating and just scattering our light all over the place, which led to no coupling because there was no light in the cavity at the end of the day, right? Our quality factors were terrible. So Ovacek spent many months trying to work out the conditions, the spinning conditions and some of the chemistry to get it so we can have decent films. And that's still really the challenge, right? Is getting the platelets to be a really good uniform film in there. But he got that worked out. And then, you have to hit this thickness, right? So he also spent some time making curves like this, and this curve will change every time you change the loading of the platelets, but this is a spinning curve. So for a given spin speed, what thickness of PMMA and platelets do you get? And so you can kind of, at this point, he's got it pretty well down that you can kind of hit, the 2000 to 2500 range, and you'll get something that'll work for the cavity. Okay? So it took all that prelude was just to get it to the point where you have these cavities. Okay? But at this point now we have some cavities, and so we have our platelets with a photoluminescence around 2.4 EV, and then we design these cavities to have a cavity mode resonance similarly, right? So if you look at the reflectivity, you see a huge dip right there in the reflectance where you hit the cavity mode. And our quality factors, generally speaking, are around 2 to 300 or something like that. So they're not the greatest cavities, but they're not bad either, right? But now we need to actually do one more thing to characterize the cavity, and that's do a Fourier space spectroscopy, right? And so this is like optics speak. So we have an optics institute at Rochester, so they always use this fancy language like Fourier space spectroscopy. For those who want a translation, this is just a microscope, okay, basically. So they make a microscope. So the idea is that the sample is down here, and then you have a microscope objective. And what the microscope objective is designed to do is it takes in the image of the sample and it reproduces it at the back focal plane of the objective. So we take that image and we send it through what's called a tube lens. Now, if you have a microscope, and we have a lot of inverted microscopes in our lab, the tube lens is part of that, right? But here, this is just showing you the guts of what's there. The tube lens then takes that image and focuses it, or projects it onto the entrance slit of your spectrometer. Okay? And then the spectrometer just naturally takes that image and then disperses it on a CCD. And if you have a mirror in your spectrometer like we do, then you just get the two-dimensional image of what's at the Fourier plane. But if you put the grading in, then in one direction you get energy information, and in the other direction you get spatial information. So you can actually then map out spatially the energy difference of your cavity. And why that's important is because as you start looking at different angles away from the normal, the mode of the cavity, the energy of that mode changes, right? And so this is well known, right? And so there's the data. So as you at the zero incident angle, you're getting this 2.4 EV resonance as shown here in the middle figure. But as you move away, you're starting to get an increase in the energy. And that's because you're starting to include off-angle wave vectors. And so you can go through and model this. And essentially the energy as a function of angle goes as the tan squared, which for small angles is roughly theta squared. So that's why you're kind of getting this parabola looking dispersion. So bottom line is that the energy of the cavity varies with roughly the angle of incidence or collection of the light squared. And the dotted line here, the TMM, just to complete the figure, is this a transfer matrix simulation? This is a computer simulation of that. Okay, so now we're going to put in the platelets, and for decades, many years, going back to legends at Emil Wolf and Leonard Mandel at Rochester. University of Rochester has been doing kind of quantum optics, but mostly with atoms, right? And so you mentioned this a little earlier, like when you start forming polaritons with atoms, they're somewhat simple in that they only have one electronic state that couples to the cavity. So for example, you have the ground state of the atom, and then you have with one photon in the cavity, or n photons, let's say, and then you absorb a photon, so you may have 0 now left in the cavity, but the atom's in the excited state. And what you end up doing is forming polaritons, upper and lower polaritons between the atomic states in these photon states, right? And then the coupling strength is measured by something called the Rabi splitting, right, which is usually written as omega, and that defines the separation between the upper and lower polaritons. Things get a bit more complicated though when you start looking at things that are bigger than an atom, right? Because now let's take our platelets. Our platelets have not just one state, but they have a dispersion of energies for their exciton, and for now there's a dispersion of energies for the photon. Now, on this scale, since the photon is effectively so much lighter than the exciton, the photon energy is varying quite strongly with wave vector as that, theta squared, right? Whereas the exciton at these wave vectors is just basically flat. So what you have is a hybridization, right? A mixing of a kind of a flat dispersion exciton with this k squared, roughly, or theta squared photon. And when you mix those two, in the language for those who know Roald Hoffman's work, you're getting a band repelling. So these two bands will repel each other. They never cross when you form hybridized states. This is also known as an anti-crossing. And so you get an upper and lower polariton branch with a dispersion that shows here. So far away with large wave vector, it looks like an exciton. Far away, a very small wave vector looks like an exciton, and then in between, the upper one, and then the photon looks like the upper branch at large wave vectors, and the exciton looks like the lower branch, lower wave vectors. So that's what the dispersion is expected to look like. So when we throw the nanoplatelets in the cavity and measure that, we're seeing two branches. So that was exciting, right? So this is our first time we've seen strong coupling with the platelets in these dielectric cavities. There's a little help here. Here's this dark lines here. That's the upper polariton branch. Here's the gap right here at an angle roughly 15 degrees or so. And then this is the lower polariton branch. So you clearly can see two branches in the reflectivity. When we went over and looked at photoluminescence, however, though, we only saw one branch luminescing, which is not uncommon, but that's also what we saw. So the solid lines here are the exciton and the cavity, and then the dotted lines are where we expect the polariton branches to be upper and lower, and we're getting photoluminescence just from the lower branch. So we really want to understand all this, right? Why are we getting photoluminescence from only the lower branch? Why are we getting only photoluminescence at these really high angles? And then why is the reflectance kind of from the upper branch also at these really high angles, and we're not seeing much here from the upper branch at the lower angle? So we want to understand all that. So we turn to our theorists, right? Who have spent some time really getting into these models. And so let me walk you through some of the models. So the Janus-Cummings model is just the atom in the cavity model, right? Single atom. Tavis-Cummings model expands on this and says, okay, if you have n emitters in the cavity, such as n platelets, right, that are coupled, then these n platelets will couple to the cavity. You have upper and lower polaritons from those n platelets, a single coherent state. But then you have n minus one of these platelets are, and the terminology for this is dark. I don't like the terminology being dark, frankly, because they're optically allowed transitions, but in the cavity they're uncoupled. So a better term would be uncoupled, but the dark is is what people use in the literature. So we'll stick with that for here. So dark states, right? So you have n minus one dark states. And so you can put all this together, and what Frank came up with in terms of his Hamiltonian is 4 terms. So I will spare you all the details of the Hamiltonian, but there are 4 terms. There's a term that corresponds to the electronic states, the exciton states of the platelets. There's a term that corresponds to the cavity quantized mode. There's a term that deals with the light matter interactions, and then there's just a laser field that's classical. So the platelets have a complicated electronic structure. We just chose a 3-level system. So laser pumps high up in the conduction band, and then it decays rapidly, non-radiatively to the heavy hole state, and that's the state that's going to couple to the cavity, right? So we don't include the light hole state, and we don't include, but we do include exciton photon couplings, and they'll be very important, as you see in a minute. The photons in the cavity is just a standard, n plus 1/2 h bar omega. So if you remember your harmonic oscillator Hamiltonian from quantum mechanics, that's the same Hamiltonian. And then there's also, he includes the light matter coupling, and so the coupling strength usually is written as G, and it depends directly on the oscillator strength of the transition. So that's again why we wanted to use platelets. Depends inversely actually on the square root of the volume of the electric field mode in the cavity. It's another reason why we wanted to use really thin cavities and confine that mode to small volumes. So you can get the Rabi splitting is just the square root of the number of platelets that are coupled to the cavity. We got roughly 1,400 platelets coupled. You throw in reasonable parameters for the laser energy and the coupling strength, and you can obtain analytical expressions for these energies and eigenstates. And so here you go is what you end up with. And so these dotted lines are the expressions of the calculated expressions of the upper and lower polariton branches. And the theoretical fits do a pretty good job, right? We get an 83 MeV Rabi splitting, and we get that the detuning, which is the difference between the cavity mode resonance at 0 angle and the nanoplatelet exciton resonance at 0 angle, that detuning is around 130 MeV, and that fits, then allows us to fit these two branches here. I think more interesting though to me is this photoluminescence, and I'm just so impressed with the model. Like Frank's model just nailed it, right? And so these dashed lines of the model again for the upper and lower polariton branch energies. The bottom line is the theory, and you could see the theory captures that the photoluminescence should be at this high angle, and it captures really well the asymmetry in the upper and lower polariton branch photoluminescence, right? Like the theory predicts that you should have strong luminescence from the lower branch. Now we've repeated this experiment, a few times, right? Every time we get a new cavity, it's not exactly like the ones, because we can't make it 100% reproducible. So the cavity mode varies a little bit, and that allows us to vary the detuning, right? And so we can vary the detuning from hundreds of MeV, shut down to 35 to 30 to even only 16 MeV. And what you see in the photoluminescence is that the photoluminescence starts at these very high angles when the detuning is large, but as the detuning starts to get smaller and smaller, you see the photoluminescence now comes from the entire lower branch, polariton branch. And this is for all the same Rabi splitting, right? So this is really just an effect of the detuning. And this is modeled by theory, right? Again, like they just nailed it over there in the theory section. So you get these high angles photoluminescence when you're detuned, and then as you start to get in resonance with the cavity at 0 angle, you see the whole branch emitting. So, it's all captured with the model, right? So we think we have the model working pretty well to understand. So now we can try to say, okay, well, what physics can we understand now that we have the data modeled pretty well? And so let's revisit what this Travis Cummings model, right? So there's no phonon fluctuations. You just have these n-1 dark states at the exciton resonance, and then you have these coupled states, these n oscillators, these n platelets coupled to the light, giving you these upper and lower polaritons. And so at large angle, then you're directly in resonance, whereas at small angle, the exciton resonance is shifted away from directly beneath between the polaritons. So what Frank's group does is, this is Archigid, he then goes and does quantum dynamics simulations. I've called them the spaghetti plots, right? Because what he's doing is he's coupling to vibrations, and then he runs a trajectory and sees how the upper and lower polariton branches couple to these dark states, and then he runs another one, then he runs another one, and keeps almost like Monte Carlo, and keeps repeating this. And what you see is that when you're at small angles for large detuning, the lower polariton, while it has all of the photonic character, is not seeing any of these states. It's not seeing the dark states. It's not seeing the upper polariton branch. The phonons can't mix these three together, and so you don't get any emission. Everything is dark, right? Whereas at large angle, the upper and lower polariton branches are much closer together, and they're coupled to the dark states. I mean, look at all the blue in these dark states. They're coupling through this with significant photonic character, right? And so what this physical insight, is telling us, right? This model is telling us is that it's the vibrations, it's the phonons that are actually really important. And in the Travis Cummings model, they're neglected. But here, the dynamics is telling us that it's the phonons that are mediating these transitions between upper and lower polariton branches through the dark states, right? So if another way of saying it is, the dark states are brightened by the phonons. And then you can go through and look at actual dynamics. And so for both the small angle and large angle, you can map out the population of all these different states. So the ground state, dark states, upper and lower polaritons. Let's focus on the dark state here. Let's say at these large angles, right? Initially, it grows in as the nanoplatelet relaxes back to the heavy hole, and then it slowly decays away, transferring population, in this case, to the lower polariton branch. The upper one stays pretty unpopulated, and this is why you see the photoluminescence there at these large angles, because it's the lower polariton that has photonic character that allows it to emit. The converse is true at small angles, right? The upper polariton is populated, but it doesn't have any photonic character. So what you end up with is that the photoluminescence intensity near the resonance is determined by, really the photonic character of the branch, the upper or lower branch, and then these phonons that are mediating those transitions. And then there's also cavity loss. So that's why the quality factor comes into play, because obviously if your cavity is really lossy, then you'll decay out of this state before you can really emit. Okay? So those was some physical insight that was really only possible from Frank's calculations and the nice synergy we have modeling between the experiment and the theory. Now, recently we've been able to get room temperature strong coupling, and so it's not as good as at low temperature where we got 80 MeV. Here we're getting only 50. We're working on doing better. The reason why we want to move to room temperature is to start to think about applications, right? And so we're really thinking about polariton photochemistry. So photochemistry has been around for a long time, right? Over 100 years. I think Art Noyes was at Rochester. He was one of the greats at Rochester, and he was a photochemist way back 100 years ago practically. But polariton photochemistry is a little different, right? And this is kind of a theorist way of looking at it, is that if you have, let's say, a dissociation for a molecule and you photoexcite it, like you can end up on this upper potential energy surface, and then you just sort of slide away to infinity and the molecule may dissociate, right? As an example. When you start thinking about forming light matter hybrids, though, what you end up doing is copying the ground state potential energy surface and mixing it with the excited state one at an energy raised up by the photon of the cavity, the photon resonance. So as diagrammed here, you can start to get some local minima that you wouldn't get in the excited state normally, right? And we are clearly not the only ones looking at this. This field is getting very crowded. And so there's a number of papers that have come out in the last 5 years or so, mostly theory, actually, almost all theory, that have talked about manipulating chemical reactions using polaritons. And so, here's some papers here on adiabatic dynamics and changing things. You can predict that you will either accelerate or suppress isomerization rates. There are new conical intersections, right? New conical intersections means potentially new photochemistry, modifications of charge transfer or singlet fission, and then, modifying reactivities in the ground state of molecules. And beautiful work by Ebbison in this paper in Science on doing that in a cavity using vibrational polaritons. And we started to see these papers come out, and we were working on polariton photophysics at the time, actually, and so we've had a long interest in putting things in the cavity. So my students went and dug up this paper, and they said, "Oh, you were working on cavities for 15 years," made me feel like I've been here a long time at Rochester. So we worked with Mikhail Lipson and down at Cornell, and she made the microcavities, and we were looking at two different colors of nanocrystals and putting them in a cavity and then increasing the energy transfer between the red and the green and the red ones, and that's shown here in this solid to dotted line. But this is not really strong coupling. It's just the fact that electric fields are modified in cavities. You could change the output of your luminescence by changing the oscillator strength simply due to changing the field strength. But we've also had a real, since those papers, a real big interest in photochemistry. So we've been working with Carl Brennan and Al Matson at Rochester on doing solar fuels and making hydrogen out of pretty simple things like, quantum dots and nickel salts and like vitamin C, and getting really good hydrogen production. And this led to a collaboration with Dan Wykes at Wisconsin. He used to be at Rochester. He's now at the University of Wisconsin doing actually organic chemistry. And this is new for us since I never took organic chemistry. I get to learn a lot of organic chemistry from Dan, using the quantum dot to create an excited electron that can then do some chemistry and eventually gets returned. This is photoredox catalysis. And so, we were, about the time that paper was coming out, we were thinking, maybe we could take our interest in cavities and our interest in photochemistry and not just use kind of classical light, right? So light as a wave, but think about quantum mechanical light. And I know, some of my students, they're big cat fans. They don't like this picture where the cat is like in a superposition of dead or alive, right? So for those who don't like the dead cat, we can use Schrodinger's cat in the beaker, where of course you've already made the measurement on the cat. It's collapsed to the alive state because you can see it. Okay, so there we go. So this is a quantum mechanical cat. So we're trying to think of now taking quantum mechanics and applying it to these principles. And so we were so fortunate to be able to get an NSF funded CCI, Chemical Innovation Center, and we call it QUEST. It's quantum electrodynamics for selective transformations. And that's really the key, is we're trying to eventually get to selective chemical bond making and breaking, right? And so the idea is this, we were having our discussions about the center. So the idea is, we're talking with organic chemists who said, hey, what if we could do this? Like, what if you had a carbon chlorine bond, a carbon halide bond, and a CH bond, and said, I never took organic chemistry, but I think I've been around enough chemists to tell me that like this CH bond is just a strong bond, right? And they say, oh yeah, very strong. So in other words, when you do reactions, you're going to always break the carbon halide bond first, and that really limits your chemistry, right? I mean, that you design reactions completely around that principle. But we said, wait a second, what if we could, reverse it? What if we could break the carbon hydrogen bond first, right? And they all like, whoa, we're blowing their mind, right? Because you can't do that normally in a flask. And so that's our goal in this center, is really to think about, can we actually do reactions in a cavity by forming polaritons that will selectively break a bond? And so why was this even possible, right? Well, again, when we're forming polaritons, and we unlike a lot of the other papers that have come out in the literature, we're not doing ground state reactions and using vibrational polaritons. We don't think those are going to have enough energy at the end of the day. We want exciton polaritons, right? We want electronic polaritons, because what they're going to do is, when you form them, you actually change the wave functions of the matter, right? And so that's really shown in this paper from I guess it's 2 years ago now, where Narang and Flick calculated that in free space for this formaldehyde, you've got a ground state and an excited state electron distribution, but when you form the polaritons, the electron distribution changes considerably, right? And you don't even have to be a chemist to understand that this ground state looks very different than this upper polariton or this lower polariton. And so when you change the electronic distribution of the electrons in your molecule or in your atom, right, you're changing essentially the way the atom is going to bond, right? And so that in principle should lead to new chemistry, and then eventually you can see that through this figure we showed earlier with changes in potential energy surfaces. And so we haven't done the selective transformations yet. That's down the road a little bit in the center, but we have started on this, and initially we've started on trying to understand charge transfer, because we figured this is the easiest step, right? Often when a chemical bond is formed, a reaction happens, there's a charge transfer event. It's usually like step one. And so this is really Arkajit's work, and I was a cheerleader, but I can tell you a little bit about what we're doing there. And so what Arkajit was calculating was a quantum dot as a donor here. So he has a quantum dot that then gets photoexcited. So we suck up a photon from the cavity. So this D0 is an excited quantum dot. And then you form the polaritons. then these polaritons are going to transfer that electron to an acceptor. The acceptor is not in the cavity. Okay, so it's not coupled. Well, it could be in the cavity, but it's uncoupled. Okay, and you're going to see various symbols on there. And this is just Frank testing all of his different levels of theory, different models, Janus-Cummings model, rotation, wave approximation, et cetera, right? But I want to just highlight a couple things from the paper. And if there's any theorists that really want to, on the call, that really want to get into these various levels of theory, then you can see the details in this paper here. Okay? So we think about charge transfer in terms of a model from Rudy Marcus. He won the Nobel Prize for it, called Marcus theory, where you have this potential energy surface here for the free particle. The upper and lower polaritons are in red and blue. And when a charge transfer happens, right, there's a free energy difference between the donor here and the acceptor. So the charge is rattling, the excited molecule is like rattling around here in this potential energy surface, and then eventually the electron transfers over. And the driving force, this free energy difference, is an important parameter, right? Because as you can imagine, as you make the driving force larger and larger, the probability the charge transfers is more and more. And you can see that in this figure here on the right, where the rate of charge transfer increases. Kind of counterintuitively, though, as you make the free energy difference really large, it rolls over again, and so this is called the Marcus inverted regime. And this is well known from any charge transfer theory, right? So what Archegid showed is that there are regions, if you look at the vertical axis here, where for both the upper and lower polariton, you get an increase in the charge transfer rate. This is for a coupling strength of a couple hundred MeV, right? You can actually beat out the charge transfer rate from Marcus theory, or you can actually slow it down, right, as well, depending on where you are on this plot, right? So you have the possibility to actually get some fine control over charge transfer. The challenge there is that, if you're not in the inverted regime, it's hard to get there willingly, right? Because it's just really large free energy differences. So if you're over on this side of the curve, you're probably gonna have to transfer from the upper polariton to see things. And we know that the upper polariton doesn't photoluminesce, so the lifetime there is probably not the longest. So the question is, can we actually see this? And we're still working on that experimentally. If you look at the zero free energy difference and look at the bottom curve here, you can see again that as a function of coupling strength, Marcus theory tells you, of course, because there is no cavity, so there is no coupling, therefore the rate should be constant. But as you increase the coupling strength, the rate increases, and you can get up to well over 2 orders of magnitude enhancement in principle, which is pretty exciting, right? We think, as you start increasing the coupling. The challenge there is that how are you going to increase the coupling from where we are, which is 80 MeV, up to 600 or something like that? So we're working on that, and that's why we have our optics collaborators on the call on our project to kind of design cavities that will get us there, right? Because right now we're not there yet. And finally, this is another example of Archegid's calculation, where now he's varying not only the coupling strength but the detuning. And this is interesting, that as you start to detune further, you actually can get increases in the coupling strength, or increases in the charge transfer rate, versus Marcus theory, which again is no coupling. But we like this red curve because this is 0.1 EV coupling strength. We can hit this basically now, right? So we think that as you start varying the cavity detuning, we may be able to get an order of magnitude out of this over normal charge transfer in using Marcus theory. In fact, there are some predictions, and this is something we're also pursuing, that you may be able to drive an electron uphill, meaning, with when the acceptor state is actually energetically higher in energy, right? That would be classically kind of forbidden. We're not violating conservation of energy here. You would think that, but no, it's really the vibrations that are putting energy into the system, transferring charge to the upper polariton that then does the actual charge transfer. And that's this quadrant up here. So you can see there actually is some fairly decent enhancement in the rate over where you would be normally. So we're pretty close to actually seeing this, and I'll show you in a minute how close we are in terms of actually getting some data on that. So it's getting late, so let's wrap up. So the take-home message is that, we think that nanoplatelets of, cadmium selenide in particular are really, these colloidal platelets, really great emitters and really great, optical materials for, putting into dielectric cavities to create promising systems for investigating quantum science. We got strong coupling between the platelets and the cavity, even at room temperature. We saw that in both photoluminescence, seen here, and reflectivity. And the theory was really critical to not just presenting you with some numbers, but really looking at what's behind those numbers and trying to understand some of the physics. So where we're going is we're trying to understand the lifetime of a polariton. You'd think this maybe would be trivial, right? You can see fluorescence. What's the big deal about the fluorescence lifetime? But there's actually quite a controversy about this. So there's one camp that says that the lifetime of the cavity should be the exciton lifetime, because there's this cycling of the lower polariton to the dark state to the upper polariton through all these vibrations, and that's going to just make everything be the dark state lifetime. There's another camp that says, no, that's really wrong. Your lifetime is going to be limited by the shortest thing in your, in your system, and that shortest rate, the quickest rate, is the cavity photon decay, and so that's going to dominate the lifetime. And so, we'll see, right? We're making those measurements right now. I mentioned we're looking at new cavities. We want to localize the field to make it even smaller, and so that's going to help us get larger coupling strengths. We want to put the nanoplatelets exactly where the field is, and so we have different cavity designs to make us do that. And then Frank and his team are really working on getting more accurate representations of platelets, as well as trying to understand, for example, the lateral modes in the cavity and things like that to get more accurate calculations. So we're working on photoluminescence lifetime from the polariton. We have some measurements. We have some interesting data, and we're just not ready to share it yet, but it's close, right? And really the issue is consistency. So here, we're seeing in the cavity, it looks like the lifetime has gotten somewhat shorter, although, getting the cavities to be the same and the polariton densities to be the same has been a problem. And so hopefully we'll be able to report on that soon. We're also, as part of our center, bringing Terry onto the project. So Terry Odom at Northwestern has these beautiful metal lattice plasmon cavities where these metal particles are spaced in a plasmon wavelength apart, right? And so you get these beautiful resonances in the visible. And we've coupled platelets to them, right? And so in the Bayer array, you see these plasmon resonance dispersion curves that are pretty straight. You start to see these anti-crossings here and band bending when you put the platelets in. So this is a really nice system because it allows us good optical access to the top, as well as allows us to flow in liquids naturally, and it allows us to, in principle, to do chemistry a lot easier than our Fabry-Perot cavities. Okay, so I'll leave you with a picture of the University of Rochester, and Shannon may remember his time in the chemistry building down here, as well as a view of the city from the campus. Thanks so much for the chance to tell you a little bit about our work, and I am happy to answer any questions.
Todd, thank you so much for your for the presentation of your beautiful work. Questions? Yes, Shannon, please.
Thank you very much, Todd. It's a very, very exciting talk. I feel like I'm taking a quantum chemistry again with you many years after. So you touched on the liquid type cavity, the photochemistry, how challenging it is. I mean, to move from solid to liquid with strong electrolytes, especially I think you're also moving towards electrochemistry type systems. What are the technical challenges, or you think?
Yeah, that's a good question. So I mean, almost exclusively, right, any chemistry that's been done, with one exception, I think, has been on in liquids, has been on these vibrational polaritons. And the reason is that you can form, since vibrational energies are MeV, right, 1 MeV roughly on that order, then your wavelengths are 10 microns or so, and therefore, or more, right, in the infrared, right? And so therefore you can use, like in one paper, for example, Teflon spacers to keep your cavity well spaced, and then flow microfluidics to flow liquids through. Beautiful paper. We don't have that option because you see our cavity mirror separations are only 200 nanometers or less, right? So a couple answers to your question. One is we are looking at systems that we can modify the chemistry in the solid state, okay? And so one of those is charge transfer. So if you take acceptors or donors and put them together in a cavity chemically, we can do that, right? Then you can make everything in the solid state and look at the differences in transfer rate in and out of the cavity. We think that should be viable. It's not going to be making a chemical bond, right? But at least it'll prove the effect. We also have molecules that actually can isomerize, and change. They can cyclize essentially, actually better. We have molecules even cyclize in polymer, and we can put them in the cavity as well. But again, that's like a proof of principle, right? So this is where we're relying on our optics collaborators. We're looking at moving away from these Fabry-Perot cavities, which just aren't going to be what in the end what we're going to do, and we're looking to go to do on-chip cavities, right? And so making everything in silicon in the plane, and there we think we can flow liquids through a system and couple to a cavity that's in the plane. There's a lot of fabrication issues that are a problem there. Fundamentally, the challenge is that when you start thinking about making cavities like out of silicon, for example, the electric field really wants to be in the higher index material, wants to be in the silicon, and the platelets are in the air, right, or in the liquid. And so the challenge there is getting the high field to be confined where the platelets are, and we're working on that. So, I don't think in the course of our phase 1 CCI, we're going to be doing too much in the liquids, although, Terry's cavities, I think, would be a way to do it. And we're pursuing that too, actually. But I think longer term, though, we do have a path to get there if we can show the effect. The question, I think, in my mind is how big is the effect going to be, right? Is it going to really matter? Can we modify those potential energy surfaces by 10 or 20 kcals per mole to get us there? And if we can, I think then we'll figure out a way to engineer those cavities.
Thank you.
Other questions? Well, I have questions. Let me first ask a quick synthetic one. Todd, do you intentionally make your platelets square, or is that something your recipe produces?
So the recipe that we borrow produces square ones. However, Willie is spent, he's a couple years, he just likes to play with the platelets. And so we have several other recipes that give platelets with different surface areas.
Mm-hmm.
And we're using those too. The basic physics is not that much different, right? Although you can tune the energy a little bit with the platelet width as you make platelets more and more looking like bricks, let's say, right, more and more narrow, then that energy blue shifts a little bit. It also affects some of the exciton photophysics and slightly, right? So we didn't pick the square ones intentionally, but that's just what we had good luck with, so we've been using those. But we could move to other ones if we wanted at some point to kind of fine tune things.
Okay, and now within that model where you put, say, 30 platelets in the cavity, are they isolated from one another?
Yeah. So yeah, the platelets are in the polymer. We make them as thick as dense as we can make them. So it's a sludge, So it's a polymer platelet sludge that we put into the cavity. We only couple, as you saw, about 1,400 of them in this one collective state, and so we're thinking about doing a better job, and that's something that Overcheck's working on. Is how do we get more platelets into the antinode of the field, right? Because right now we just spin and they're everywhere, and so there may be some platelets that have stacked. I don't know. The polymer may keep them apart, but we really want them also ordered. If they're this way, then they're uncoupled to the cavity, right? We want everything in plane. So there are ways of doing that, and we haven't honestly been too smart about it, but we're trying to be a little smarter and a bit more elegant, because I think it'll help. So he is designing new parameters for spinning and deposition and things like that to get them where we want. The new cavities, I think, will also help, because when you start having the cavity fabricated in the silicon, then you can just drop the platelets where you want, and then it should be easier in principle, although we may find other challenges there.
Yeah, well, I know how much platelets love to stack. That's why I can see how challenging it can be to have them isolated and sitting face down on the surface. And another question that I have is, you said that the upper and lower polaritrons are coupled with phonons. I assume, are those LO phonons of cadmium selenide?
Yeah. So in the model, Frank, we sat down and said, okay, what's the essentially the Wang Riz factor, right? What's the coupling strength of the LO phonon, which is going to be the major one, and then how does that couple in the free space? And then he just put those parameters into the cavity calculation. So yeah, that's what we would consider to be the dominant source of phonon coupling. I mean, there is also other acoustic modes, but I don't think they couple as strongly.
Well, and you would need many of them also, right?
You could, yeah. I mean, the yellow phonon's got a large enough energy. That's the one that we put into the calculation. So it's kind of serving, as we said, like to take the dark states and kind of brighten them in a way and couple them, because like normally they would be completely uncoupled, right? So that kind of mixes everything up, and that's actually important because it allows us to get population in the upper polariton, which then could do some chemistry.
But it looks like it takes about 3 LO phonons of cadmium selenide, given if they're 26.5 MeV, to couple them.
Well, the Rabi splitting is 80 right now, but the dark states are in between, so it may take less because you're hopping up and down.
So it's through that intermediate dark state. Okay.
Yeah.
And did you happen to see if you're in perfect resonance, if your, say, upper middle state separation is 26.5 MeV or so, you have an enhanced coupling?
No, that's a good question. Is there are some papers that for not the platelets but other systems suggest that when you are at a kind of a phonon resonance, right, that you get enhanced coupling. We haven't looked for that. It would be interesting to look for, though, because honestly, it's easier to make smaller Rabi splittings, right? So getting something around 26 or 50 could be easier than getting higher. We've been pushing higher for the chemistry, but that's an interesting question. We'll have to think about that for some of the photophysics projects.
Well, thank you very much, Todd. Any other questions from the audience?